my first talk, I took us from about 1900 up to 1948 or thereabouts. I propose to start this one around about 1946 and then come forward to the present day. Just to remind you that it was the 1st of January 1946 that 6 people from the Ministry of Supply, a scientist, an engineer, an administrator, a security chief, and a couple of other people walked through RAF Harwell's front gates, and it became AERE Harwell from that moment on, 1st of January 1946. They immediately set to bring teams of people in to start building the first nuclear pile to be erected in this country, which was GLEEP, Graphite Low Energy Experimental Pile. So important was this project that Clement Attlee, the Prime Minister of the day, diverted scarce supplies of steel from London, which they were going to be used for rebuilding the Houses of Parliament from the Blitz. They were diverted to Harwell in order that this reactor could be constructed as quickly as possible. And the team under Watson Munro really moved very quickly and got an operating pile going within about 15, 16 months. And it went critical in August 1947. And by Christmas of that year, it was already, apart from producing scientific data, was also producing radioisotopes which were being used in the Oxford hospitals. At the same time that GLEEP was being constructed, a second, much larger reactor, BEPO, British Experimental Pile O, was constructed in Hangar 10. GLEEP was constructed in Hangar 8. And BEPO went critical in 1948 and was to remain in operation for 20 years before it was shut down. GLEEP, I should say, carried on working for 43 years and wasn't shut down until 1990. And in its last days was used as a calibration standard for nuclear instrumentation to be used on reactors throughout the world. So GLEEP had a very long and uninterrupted history, and BEPO had a short but very useful history because it was the precursor of the wind-scale piles, air-cooled Magnox reactors that in those days was designed for producing the materials for the bomb program. Whilst the reactors were being built inside the hangars, there was frenetic scenes of activity throughout the Harwell campus. And here we can see an overhead of the firm of Chivers. I think I showed something like this in the end of the last talk. This is a slightly different view. You can see up in the top right-hand corner a coal-fired power station, which is the location of building 424. In the foreground, you've got all these underground trenches and air ducts supplying air to the BEPO reactor. And this is the exhaust stack, the BEPO chimney, originally designed by the Ministry of Supply to be an octagonal-shaped chimney. But Chivers felt that he could make it quicker if he allowed his men to build the traditional round one. And there they are, going round and round and round, taking it up to 200 feet. There is a story, and I believe it to be true, that when they turned the fans on for BEPO to get the original air to go round the system, just to check it out, that the 200-foot high chimney emitted a note like an organ. And it was heard all over South Oxfordshire, a booming noise. So they turned the fans off. One of the scientists on the project rushed home to his prefab and got a set of tuning forks, came back after lunch, and they switched it on, and he worked out the frequency of this note. From that, he was able to look at the drawings and work out where they should put impedances to the flow of the air to disrupt the nodes and all that scientific bit to prevent the note from sounding. Part of the problem was due to the fan mountings, which were supplied by Vickers Armstrong. But within a couple of weeks or so, they'd solved the problem. The world's largest organ pipe was silent forever. Lot of RAF infrastructure in those days. This is a view of the tank farm taken much closer in history, but all that down there, the RAF sewage works, we kept it in operation until quite recently. I like this photograph. It's got a 112 Newbury to Oxford bus going up the old A34 outside the fence. So we added all this structure to deal with all our liquid effluent in the years afterwards. But the RAF sewage works was to remain in operation for 50 years. There's an early shot here I'm not going to name all the scientists in the picture, just to say that that is Sir John Cockcroft. There are people like Blecher and Vick, and I think that's Schonland there. But the man I want you to look at is Dr. Klaus Fuchs, who was the head of theoretical physics. He would be the equivalent today of the head of ISAT, because he was in charge of computational analysis. No computers in those days. It was all done by hand-cranked machines, and I was taught in 1960 how to do long division on a hand calculating machine. Just briefly, he was a German who was naturalized British in about 1939. He was picked to join the Harwell team because of his theoretical physics capability, and it was a great surprise to him to be arrested in 1951, where he served a number of years at Her Majesty's leisure. This is a picture of Mavis Waldegrave, who's alive today, aged about 84 and living in Southern California. She is loading into an inner core here some clad plutonium rods. And notice that she's only wearing kitchen gloves. And the outer core shielding is natural uranium. That facility went critical in the late 50s and had a breeding ratio of ×2. It generated twice as much fuel as it consumed in physical terms, in physics terms. This was followed very quickly by a larger device called Zenith, and it was the Zenith fast breeder reactor which was subsequently taken up to Doomray and became the core of the fast breeder reactor up there. I like demonstrating this one to lay audiences in particular because handling plutonium wearing kitchen gloves. I'm not going to go into any details of what this is. This is the Cockcroft-Walton generator. It just gives a picture of the type of science that was being done in the 50s in Hangar 8, next door to Gleep. In Hangar 7, scientists were constructing electromagnetic separators, and in particular, this one, which weighs 1,000 tons, and spent most of its research life shrouded in green curtains, which came down from the hangar roof and totally encased it, because what they were doing there was indeed very top secret. And when Aldermaston was created, that work was transferred to Aldermaston later. It remained in an unused state for many years. It was used as a backcloth to a film made about Oppenheimer, the father of the H-bomb, because the one in America, Oak Ridge, had been dismantled. The one at Harwell was identical, so the Oppenheimer film was created using this as a set. It was dismantled and removed from Hangar 7 about 10 years ago. But that's typical of the large items of equipment that the scientists were using. Some of you may recognize this and will know more about it than I do. But this is a picture of the sort of gear that the scientists would wear operating, I think, on the Hermes facility. Is that right? Yes, the Hermes facility in Building 220. But these were the early air hoods, and these rather black with things with knobs on top, rather horrifying pictures, but much beloved of the film industry. So that's quite an old photograph from the 50s. In 1954, having been part of the Ministry of Supply for 8 years, in 1954, AERE became part of a new organisation called the UKAEA, and this is their coat of arms. And some of you might be interested in understanding the symbology which is captured in it. This is a black graphite moderator of a reactor. These are uranium fuel rods going through it. This one at the bottom has been split, releasing energy, tremendous power. This power is restrained and chained down to the ground and is under control. There are a number of stars on the Parthenons, as they're called, and if you count all the tips, there are 92 of them, one for every element. Over the normal corporate mask you have at the top of these such heraldic devices, we have a picture of the sun with its rays, which is pointing towards fusion. Even though fusion was very early, somebody was inspired to have that in the coat of arms in 1954. And the The house martin, or the blackbird in the centre there, is part of Lord Rutherford's coat of arms. By about 1956, we were developing the electronics necessary to assist us with experimental work. This is a man called Jim Stevens, who retired from here a few years ago. Sadly, he's dead now. This is the world's first transistorized computer. We beat IBM by 6 months. It was built just entirely as a computational machine, and no serious thought of ever marketing it as anything. But it's just interesting to note that IBM produced their transistorized computer about 6 months later. So that was in building 347 and in the electronics division. A number of different reactors were built and designed and built at Harwell, 14 altogether. This is the Lido swimming pool reactor, which has a core which is you can see by peering down through all this water, and it glows with Cherenkov radiation, which is gamma rays and other radiation escaping from the fuel rods faster than the speed of light in water. And as a result, there's a shock wave which we can see in the form of a violet glow. The whole thing trundled up and down on rails. They could move the core from side to side, and the experiments were all stacked outside the tank on the floor of the building. So remember Lido, because later on I shall show you what it became. The most powerful reactors we built at Harwell were, of course, the materials testing reactors of Dido and Pluto. Although this is a shot taken in the 80s, just remind you that Dido and Pluto went critical in the late 50s, one in 1957, one in 1958. In the background you can see the Rutherford Laboratory, and this is a view taken from building 521 looking towards Dido. There's a time of flight experimental tube here. A lot of neutron scattering was done from scientists in that building there. And yeah, and the whole site is full of buildings and cooling towers. And these things originally started at about 10 megawatts, and gradually over the years, as they redesigned the fuel, they got more and more power and built the power up to about 30 megawatts. The materials they were testing were primarily for civil nuclear power stations and 1 or 2 MOD applications. And if you could replicate what would happen to a piece of steel after 30 years of irradiation, one needed to know what would happen to that piece of steel if it was going to spend that sort of lifetime in a power station, and it was suspected that steels, ordinary steels, even ordinary stainless steels, would just go plastic after a time. Well, you couldn't build a nuclear power station with that possibility hanging over you. You had to test a piece of material for the equivalent of at least 30 or 40 years lifetime. And they did that in the Dido and Pluto reactors by putting a channel right down inside the middle of the fuel rods. There was a 2-inch diameter core, and they have very sophisticated rigs which were lowered inside with the fuel rods. And of course the gamma radiation and other radiation there was very intense, and you could, in a year, you could simulate the conditions of 30 or 40 years in a nuclear power station. These are the fuel rods after they've come out of Dido and Pluto, and they would stay there for 6 months under 20 feet of demineralized water. But these canisters, which were also put down with them, contain medical instruments. And as a byproduct of the gamma radiation, you could get sterilization of medical instruments. That activity continued throughout the life of the pond while we were using it, and is being carried on today by one of our newer tenants. Only they don't use fuel rods now, they use cobalt-60 sources from elsewhere. I have to say that particular photograph has been used in just about every science textbook throughout the world. Some of you will recognize this as Building 220. It's actually a newer part of Building 220. Just wanted to illustrate that people use high radioactive materials using manipulators, that the glass windows they're looking through are at least 1 meter thick. They're loaded with lead in the glass, and that provides the gamma shielding. This photograph was actually taken in the 1980s. The Building 220 was built in 1948 to what they were reckoned at the time to be hospital standards. Corners of corridors were rounded so you didn't get contamination trapped in the corners. Paint was rubber and strippable. Scientists could walk along the corridors with their gauntlets on, and the doors would open automatically. In 1948, that was all considered pretty marvelous. And the building, as you know, has been in operation since 1948, and it's still got a few years left. Within 10 years of all this activity and investment of resources into Harwell and Risley and the other sites in UKAEA, 10 years later, the Queen opened Calder Hall, the world's first nuclear power station, which had the job of producing plutonium for the bomb and electricity for the national grid, and is still in operation. And I think that's a testament to the design and the integrity of that piece of plant. Also, 10 years after Harwell started, we had an unusual visitor. Captain Dove was flying a TS-33 something American plane, a jet plane, on his way from somewhere in Kent to somewhere in Hampshire, and his instruments failed, his visibility decreased, and he got lost. Circling around southern England until his fuel was dangerously low, he spotted a red light flashing and came down to look at it and said to himself, that must be RAF Abingdon, and landed along Fermi Avenue. The next day, it was decided that he would be allowed to take off with a certain amount of rocket assistance. And so rocket pods were strapped to the wings, and he took the plane down to the far end of Fermi Avenue, turned round. They closed the A34. 2,000 people lined up round the edge of the field to watch. And he took off down the runway with an increasing roar. The rockets were ignited as he went down, and then one of them, just as he was taking off, one of the rockets went out. So this plane, just on the point of no return, dipped. The wing hit the ground, the plane belly flopped, the undercarriage was torn off, and it roared across the open airfield towards Gleep. Fortunately, it came to a halt at the place where they were digging the pit for the Tandem Van der Graaf. There were a whole lot of Irish navvies in that pit who were furiously crossing themselves, thinking that their day had come. It was decided after that that no plane must ever be allowed to land at Harwell again, and so all the runways were made narrower. They were filled in with topsoil brought in from all over the place, and there were big signs painted in the bus park saying things like RAF Benson 10 miles northwest, RAF Abingdon 5 miles due north, do not land, and other signs which were on the bus park. So that was our first unofficial visitor, and as a result of that, Harwell stopped looking like an airfield from then on. I was a teenager at the time when the Zeta machine in Hangar 7 started capturing the world's headlines. A so-called fusion device. It had a hot plasma inside. It had a lot of electromagnetic systems. It was a bit like a transformer with one coil. The current that flowed through this torus was 200,000 amps, and that makes a plasma at that temperature. The scientific community was very excited about this, and with the sign that fusion would take place would be the detection of neutrons from the torus. And neutrons were found, but they were not fusion neutrons. Nevertheless, that didn't stop the boffins of the day to hold a big world press conference in Hangar 7 in front of the Zeta machine in 1959. And I think it was the news about that which attracted me to come to Harwell later that year, where I've been ever since. And Zeta carried on for a few more years. Eventually it was moved to Culham, and I'll show you shortly a photograph of the jet. The event was captured in a cartoon of the time by Chris of the Daily Mail, January 1958. Sorry, I was a year out. 5 million degrees of heat knocking about inside. You'd think they'd find an easier way of doing this. Curious to see that they'd got the shape of Dido in there. These three buildings have nothing to do with atomic energy research. They're actually RAF towers that happen to be on the site. And there's triple chimneys there, which I will refer to later. By the early 60s, nuclear matters became useful for other than harnessing the power of the atom. The Ministry of Works was renovating and restoring Stonehenge at the time, and this stone here had been lying on the ground for at least 200 years, and they wanted to put it back upright. They started to lift it and were dismayed to find there was a crack in it. And they didn't know how far that crack went, and whether the stone would fall apart as they lifted it. So they rang up Harwell, who supplied a sodium isotope, and they did a 36-hour exposure using a photographic plate on the far side of the stone, and then confirmed later to the Ministry of Works that it was indeed safe to move the stone, which they did, and it's remained standing ever since. So even in the very early 1960s, Harwell was being used for other work apart from pure nuclear work. The tandem Van de Graaff was constructed in 1957 and has been working ever since. It's an electrostatic generator, 12 million electron volts. It's 2 accelerators back to back, mounted vertically, and that's just outside, well, we all know where that is, and in the front of the site, outside Hangar 8, where the nuclear physics work was progressing. This shows what happens at the base of the Van de Graaff. You have a whole lot of beam tubes coming out and experiments being done at the end. And this is an example of some scientific collaboration between Nuclear Physics Division of Harwell and the Medical Research Council, which has existed at Harwell since 1948 and was Harwell's first tenant. The population of Harwell by late 1950s was 6,000, but the work was beginning to run out. This is a photograph of Professor John Lutit, who was the director of the medical research, addressing the staff from the back of a lorry, explaining why there were going to be cuts to the research program from then on. And I think he had a strike on his hands, and he was actually borrowed the same vehicle that the IPCS man had been standing on to put the counterpoints. But I used that one to demonstrate that, in fact, the golden purse of the Treasury was not going to remain open for much longer. And in 1965, the Science and Technology Act was passed, allowing Harwell and other places to pursue science which was non-nuclear and for payment from anybody who was prepared to pay us. So, for example, one of the earlier pieces of work that we got involved with, that's Dr. Bob Ottlett, and this is the Winchester round table made of wood. And one of the techniques that we were good at in those days was carbon-14 dating. Anything that lives and breathes and ingests oxygen and gives out carbon dioxide has a certain build-up of carbon-14 in their bodies. The moment that living organism dies, that carbon-14 starts decaying away. So if you have a piece of wood, which was once a tree, and you measure the amount of carbon-14 in it, you can tell when that tree was cut down. And that will give you a date for the so-called King Arthur's Round Table, which if it had been, would have been somewhere in the 8th or 9th centuries. Unfortunately, Bob Ottlett discovered that the age of the Winchester Round Table was somewhere around 1350. Just do a timeline showing the main historical background. We started in 1946, creation of the UKAEA, and in 1957 or thereabouts, NERNS came into being, and high energy physics from Harwell was transferred off to the Rutherford Lab. Lots of other organisations came into being after the Science and Technology Act. NRPB, Urenco, BNFL, Amersham International, which changed its name several times over the years, still known as Amersham even today. Aldermaston set up in 1973, and creation of separate nuclear companies, the JET contract for fusion in the early 70s, UK NIREX set up, and all these arrows coming off represent staff that left the original workforce behind this fence and became separate organisations. I'm not going to go into too much detail about those organisations, but this is the bit that represents UKAEA today. About 2,000 people all told. When you think that in about here, in the late 50s, there were 6,000 at Harwell, something like 40,000 people were employed by UKAEA. A large number of them went to form BNFL. Now, it is the Science and Technology Act which led to such a diversification of projects at Harwell. Starting off with a single mission to control the power of the atom for generation of electricity, by the 60s and 70s it was becoming a multi-mission laboratory. and the setting up of R&D clubs like Separation Processes Service, Heat Transfer and Fluid Flow. These are some Harwell scientists. I think that's a custard powder factory, looking at the drying of fine particulate matter and how to save energy in that process. We started developing robotic systems. I love the hairstyle on this one. I think that was a robot called Roman. This is a later robot, which was used eventually by BNFL. That's the business end of it down there. And some of these robots could lift a ton weight, yet turn the pages of a book. So sophisticated was the engineering and the electronics that went with them. We tended to buy in off-the-shelf robots and then adapt them for nuclear work. One of the first things that Harwell was called upon to do was to dry a whole lot of books from Hagley Hall. The library there got wet, the books got damp, and they were dried out using a nuclear device, a chamber, what we would call a rough vacuum, and some chemicals, desiccants there. And depending on how long you left them in there, the water would boil off at room temperature. That was the forerunner of the Harwell drying service. Today they've got 4 or 5 of these chambers, and they do work every day of the week, restoring documents that have got wet. When you're building nuclear power stations, you need to know that there are no cracks in the steel that you're going to be using. This is a piece from the PWR reactor. It's a foot thick. This is an ultrasonic array, and there's an oil bath. It's just like doing a scan on a pregnant woman. You fire ultrasonic waves through the oil into the steel and look at the reflections. Some of them will reflect off the back of the steel, some of them will reflect off cracks in the steel. That was part of the non-destructive testing work that was to feature so much in the last 20, 30 years. This is the Moorfield Eye Hospital, and the link between this image and the one I've just shown you is that the electronics on the shelf here is identical. Here we're looking, they were looking at the defects in an eyeball, firing ultrasonic waves, sound, just using a ring that clamps around the patient's head, a soft pad on the eyeball, press a quick button, patient feels nothing, all the information is stored in there and later analysed, and you've got a complete view of any defects in the eyeball. One of the techniques that was invented at Harwell, something called ion implantation, which has the capacity to change the surface characteristics of steel objects, making them 10 times as hard. This is an artificial hip joint, which allows the patient to have that joint in their bodies for 20 or 30 years rather than just 10. We were doing work for the confectionery industry, Maltesers. There is a customer resistance to Maltesers if they start developing rims around them, because they're made by a pair of rollers, and as they fall through they come out as perfect spheres. But when the rollers wear, there tends to be a rim. So these cost a lot of money, about £50,000 a pair, I believe. They were brought to Harwell in pairs, ion implanted using our nuclear facilities, hardened, and we helped to keep the price of Maltesers down, or to put somebody else's profits up. Number of techniques deployed by scientists for analysis. These are laser beams. This is what lasers can do. That is a human hair, and that is a hole drilled through the middle of it. So a vast range of techniques developed at Harwell, nuclear work originally, and used in non-nuclear ways. This is an aerial picture of Harwell in the 80s, showing the original RAF control tower still in place, Hangar 7, Hangar 8, Hangar 9, Hangar 10. There's the water tower and the usual view to the north. And we just started to plant trees, and the place is looking quite green now compared with those early RAF photographs. NDT techniques looking for cracks was applied to the aviation industry. There are Harwell scientists from the NDT Centre in a hangar. I think this is at Staines, I'm not sure, Heathrow rather. This is the jumbo jet, and they're looking for cracks in the fuselage, micro cracks. And it became part of their airworthiness certificate that they had these tests done. Developed a whole range of exotic and exciting materials at Harwell. These are car components. Some of you will remember that in the 1970s, the Arabs increased the price of oil by a factor of 4. And automobiles, as the Americans would call them, were deemed to be rather heavy, and if you could cut down the weight and improve the internal combustion engine, you could get more miles per gallon. That is a car spring, and it's made of glass. Well, not all glass, it's glass and metal fibres. So the whole range of composite materials that were developed for nuclear power stations were being applied to British industry. Measurement techniques meant that we could do atmospheric analyses of smog and pollution. And in 1984, the most polluted part of London is around Buckingham Palace. There's a constant stream of tourists in cars and taxis going round and round those buildings. And these are the nitrogen dioxide levels in London in 1984. This is a technique called plasma-activated vapor deposition. What we've got here are nylon guides from a spinning mill through which passed nylon thread at 750 miles an hour. So faster than the speed of sound, and these nylon guides were wearing out too quickly. They had to be replaced. They had to stop the mill. So these are being nitrided in a PAVD system at Harwell, and were sent back to the mill, where their lifetime was increased by at least a factor of 10. There was a contract won to look after the works of Big Ben. This clock was made in the year of our Lord, and there's a date there of about 1850. And the whole lot fell to bits through metal fatigue in the 80s, and scientists from the NDT Centre went up to London every year when they put the clocks back in October, and deployed a range of NDT techniques looking for metal fatigue. Unusual artifacts came to Harwell for examination. This is a silver dish which came for examination from Sotheby's, a Sotheby's security agent, and that was the lady in charge of it. They were interested in knowing whether the figures round the rim of the disc were carved out of the solid or made separately and soldered into place. And we were able to tell them that they were soldered in place using hard solder techniques which were unknown to the archaeological world. They didn't realise that Roman silversmiths of the 4th century AD had these metal techniques. This one dish is part of a hoard of treasure called the Sebso treasure. That dish is worth then £10 million. We had the whole of the treasure came to Harwell over the course of a year under armed guard, and it was x-rayed and analysed without scratching it. That was the important thing. In 1988, there was a horrific accident in King's Cross, where the escalator caught fire from a cigarette end dropped by a passenger, and a tongue of flame shot out of the escalator 2 minutes later and incinerated 31 people. And there was a big controversy over the cause of it. In the frame were the people who made the chemicals, the chemical paint, the plastic paint, so-called fire retardant paint in the roof. Did that catch fire? Was there a fireball? The problem was solved using the Cray supercomputer. We would laugh now at its capacity. The supercomputer at Harwell, the world's largest supercomputer at the time, had a capacity of 2 gigabytes. Most of us have got 40 gigabytes on our hard drives on our PCs these days, but 2 gigabytes was really big stuff in those days. And armed with very little information other than where the fire started and how hot it got after 2 minutes, and this was obtained by charring measurements by the fire brigade, they calculated by dividing the whole of the tunnel up into cubic meters of space, working out all the equations of motion and heat transfer, and working out where the fire would have gone. And they postulated that the fire lay down in the trench. People were concerned. They said that the fire was being fanned by the underground trains rushing past near the bottom and pulsing the fire from below. That was wrong also. What you had, in fact, was a standard chimney. You light a fire underneath it, you get a draft going up the chimney. And that will still be the chimney effect even when you turn the chimney over to 30 degrees from the horizontal. What you've got here is an enormous chimney, sucking air from the underground system, coming up these other escalators and spiralling over, feeding the fire, and the result was a spiral of flame, which was known as the Harwell trench effect. That discovery changed the outcome of the public inquiry and led to the banning of smoking and the use of wood in the London Underground system. whole range of other techniques were being used. This building was being used to refurbish cancer therapy units. That's a cobalt-60 source being replaced. The work on plastic batteries, you can make them any shape. You can have a domestic television receiver, fill it up with plastic battery, and you've got a power source that will last 6 months. But of course the military are very interested in those sort of portable power sources, and ones which are bulletproof. You can shoot right through a plastic battery and it will still function. So that work became a core activity, and quite a secret one at Harwell, lithium-ion batteries research in the late 80s and 90s. Work which of course was taken on by AEA Technology in due course. I shall never forget the Easter of 1989. Two electrochemists, Fleischmann and Pons, announced to the world at a press conference that they had controlled thermonuclear reactions in a test tube. They had generated fusion in a test tube. And this was staggering. I mean, jet was costing £75 million a year just to operate as a research tool, and yet these two guys were claiming you could do it in a test tube. And it was the last piece of, I would say, blue skies research that scientists did at Harwell before the great organisational changes of the 90s. For a period of 3 months, £300,000 was spent and over 100 scientists were deployed looking for fusion in these Fleischmann vessels. We had the world's press were camped outside the main gate for 3 months. I spent most of my time taking video teams, camera teams, around the nuclear physics equipment down at 418. And in the end, a paper was published which showed that there were some electrochemical effects going on, but it was not fusion. I think it was 1991 that Harwell's Cray supercomputer, the Cray 2, you never switch these things off. You always leave them doing something overnight. And the common task supercomputers used to do was generating and looking for prime numbers. And lo and behold, overnight, Mike Schomburg, who was in charge of the team, discovered that it had generated the world's largest prime number. A record which we held for about 2 years in the Guinness Book of Records. The Americans never forgave Great Britain for beating their record, and they actually made it a project. Nevertheless, for a while, we had generated the world's largest prime number. This is one of the last bits of work that came in before the organisational changes. That is the compass bowl from Gypsy Moth II, Francis Chichester's world-beating boat, and the dial had radium figures on it, so it could be seen at night time. But the oil in which it was mounted, there was a leak, and oil was dripping out, and they needed to replace it. It's since become a trophy for some competition, known as the Chichester Trophy. It actually came to Harwell in 1991, and under health physics controlled conditions, the oil was drained out, checked for radioactivity, and replenished. That's a piece of history which came here just over 10 years ago. I said that the reactors were shut down in 1990, and that was the point at which we started major decommissioning of nuclear facilities. Remember the picture of Lido, the swimming pool reactor? By 1993, it was looking like that. We still kept the life belt. One of the largest buildings at Harwell, called Building 351, was actually known as White's Elephant, after the head of chemistry division. I think he was a Mr. White. He wasn't a doctor, Mr. White. They built a 7-storey building. The original design, I only learnt this last week, called for 3 chimneys 30 feet high. Remember the cartoon that Chris drew in the Daily Mail? He had triple chimneys. That was because he obviously had seen some design somewhere showing 3 tall chimneys at Harwell. After the first one was built, when it was up here, Cockcroft looked at it and said, we're not going to have those, they look dreadful. So he ordered them to be sawn off, and they've remained at that length until the building was demolished. One of the largest buildings at Harwell became a big decommissioning project, which Tom was mentioning in his last talk. And the project and the process of decommissioning was to remove all the nuclear experiments, piece by piece, room by room, and then in the end it becomes a standard demolition job. And here they are pulling out the overhead crane, which is the easiest way of taking it out of the building. It tends to destroy itself on impact and saves on cutting up time. The reactors were shut in 1990. This is a picture inside Dido in about 1989. You can see the complexity and the amount of experimentation and plant that's installed. There's experiments on every floor from the top to the bottom. Decommissioning took place almost as soon as Dido was shut down. They removed everything that could be removed from the reactor, including the bits on the outside, where a nibbling device came and munched up the Dido blister. And when all that work was done, this is what it looked like. And it will stay looking like that for the next 30 to 40 years. But the radiation levels in there are so low now that you do not require to put on overshoes or whites or anything like that. You can take in parties of visitors and stand them on the top of a dead reactor, and they used to get quite a frisson from that. All this demolition resulted in a lot of waste, a lot of conventional waste. And the cheapest thing to do with concrete is not to move it away in lorries, but to reuse it in situ. So we had a crushing machine down on the reactor site for a year or two, chewing up all the concrete being removed from the demolition work, and we used that as infill material to fill up all the voids, tanks and drains that we were removing. Because by then we were in the middle of a £25 million infrastructure renewal programme. The decommissioning work generated a lot of wastes, and these were being stored in tube stores, tubes set into the ground where there's a vast concrete block, and up to 4 cans, one on top of each other, being placed in these tubes. That's an interim store that was in operation in the 1980s and still in operation today. And it's a separate lecture, but the wastes stockpiled at Harwell are to be repackaged and put into a new store. And this is the retired chairman, as he is now, looking at the retrieval machine, which is part of the kit required to take out of those tubes radioactive cans, some of which have gone rusty. That's setting up the cell line on the new Volt store. That was taken a couple of years back. Again, the familiar leaded glass windows and the high active handling cells where the waste is repackaged. I'd like to contrast all that radioactive waste with the proximity of children. And we've had a nursery on at Harwell for over 50 years. And it was the first of 6 new nurseries to be commissioned by Berkshire County Council, as it was in those days, in 1948. And because the Harwell scientists were arriving and living in the prefabs, and lots of young kids were coming on the scene, it felt it was necessary to have a nursery creche, a nursery school on the Harwell campus. And there it has remained until this year. It's due to finish in the autumn, but the places are being transferred to Chiltern and Harwell primary schools. Again, the subject of a separate lecture. This is a view, of course, of the southern storage area. There's the Chiltern Primary School, again only about half a mile from the security fence, and private houses, formerly lived in by scientists, now lived in by members of the public. An 18-acre site that we used for storing waste and chemicals, and which we have now been digging up over the past 2 years. Just to remind you, that's the garden centre on the other side of the road, the horse and jockey. The new A34 goes across there, but it used to thunder past the main gate. So decommissioning a piece of land like the southern storage area was an interesting problem. First of all, we had to get rid of the bomb bays. These were the stores that we used for storing all sorts of materials in, some of which was radioactive. And the first thing we had to do was to make sure that they were not radioactive, and here they are scrabbling the floor with the machine, and the men are being protected not so much from the radiation as from the dust, because the levels of radiation in those bomb bays was actually quite low. But you can see outside the earth walls that surrounded the bomb buildings. That work was started in the late 80s, and by the middle of last year, when we started digging over all the soil at the southern storage area, that's where those bomb bays buildings were, inside those blast walls. This is the original RAF concrete end walls. And of course the works at Harwell over the 50 years before we started doing this work had generated piles of material from the foundations of new buildings, which we had deposited on the southern storage area in places up to 35 feet deep. And the program that we've been doing there for the last 18 months is systematically going through all that soil, bucket by bucket, looking for radioactivity, looking for dangerous chemicals, and looking for munitions. And we found all of those. Paul found this, which is a 350 kilogram bomb casing from a clutch of about 7 bombs that were dropped on RAF Harwell, mounted as trophies outside the hangars and the commanding officers' windows and painted white. When the scientists came in 1946, they removed these bomb casings and threw them down the bomb dump and then covered them over with earth, where they remained unknown for the next 50 years. We found things like this. That's very complicated. It's an anti-tank mine. We found practice bombs. We found rounds of bullets, thousands of them. We found photo flares, the things that you drop by parachute and which light up the sky. We found hydrostatic fuses, depth charges. We found everything on the southern storage area except torpedoes. All safely disposed of and now gone. An earlier photograph I showed you Hangar 9 as part of one of the 4 hangars. And we've turned that area into a natural area of conservation. And there's a lagoon there, one of 3 at Harwell. And that balancing lagoon is there to deal with the problem we get from heavy rainfall. If we let all the rainfall from the Harwell site disappear down the Letcombe Brook simultaneously, it would flood East Hendred. There'll be complaints from the natives. So we hold the water back for 4 or 5 hours and let it go rather more slowly, and that way we can deal with it. If you're spending £1 million knocking down a hangar and decommissioning all its contents and removing it, and then you've got the problem of just grassing over what you've got left, you have the choice. You could either spend £100 on ordinary lawn seed, or you can spend £1,000 on meadow grass, and you end up with a rich variety of meadow grass which attracts insects, bird life, and the rest of it. The difference in price of the seed is immaterial when you're spending £1 million. Also, you save money by not having to cut it. You cut it twice a year, make pathways through it for the staff to walk on. You leave it to go through its natural cycle, and you save on grass cutting. And I always think it's interesting that the environmental restoration practices actually save money in the end. Over 7 species of wild orchid have now been discovered at Harwell. This is a pyramid orchid. This is a bee orchid. We have other wildlife that visits the site and has made it its home. Muntjac deer at the back of 521. And they are, I can tell you, that at the back of Hangar 7, in the shrubbery there, and they're certainly on the reactor site and other places. Sometimes rather more exotic visitors arrive at Harwell, and we had a pair of peacocks from a nearby farm called Goring and Streetley were their names. The staff adopted them for a while, but the problem is if there was an accident on one of our roads, we would be liable, and so they were recaptured and their wings clipped. There's one of the early RAF buildings, coming up last slide, one of the early RAF buildings, BMS, which was a hostel in the 50s and 60s and 70s. It then became the headquarters of Nirex, and in May 2000, it became the headquarters of Oxfordshire's largest innovation centre. There was something like getting on for 30 companies located there now, and they've created 120, 130 jobs in just over a year. These are the small companies that we are attracting. Hopefully they will grow and move on to the site, take over some of the empty buildings that remain here, and produce work and jobs in the future. And this is the view, the way Harwell will be looking in the next 50 years. Modern buildings, that's built in the year 2000 and represents the Gemini building on the new development plot just outside where the Tandem Van der Graaf is now located. Thank you.